Okay, so chapter 9, which we're not really going by chapters so much, but this is what comes after balancing reactions and predicting products, is something called stoichiometry. It's that weird looking word, stoichiometry. And stoichiometry really is just mole to mole ratios. Now, you don't know what that is yet, but we will talk about that. So this is used to predict, given set amounts, how much stuff you can get out of a chemical reaction. Like if you mix these two things, theoretically, how much product can I get? Or if you make this much product, how much reactant must have been there, okay? And it's kind of like a recipe. So let's look at this chemical reaction with oxygen reacting with hydrogen to produce water. And this is balanced. So first thing, this is last topic, what kind of reaction is this? An element and an element combining to form a single compound. What kind of reaction is that?
Synthesis.
Synthesis, good. This is a synthesis reaction, okay? Now these coefficients, which are the numbers out in front, are termed mole to mole ratios. So what this means in words is that you have 1 mole of oxygen gas and you have 2 moles of hydrogen gas to produce 2 moles of water. That's how it is read. They're considered ratios. So this is how they combine. And this is kind of like a recipe if you want to make something, right? So if you want to make cookies, you have a set amount of flour you need and a set amount of sugar and whatever else, baking powder, whatever else you put in there, but they're put into to there as perfect ratios. So like if you change one, you have to change the other one respectively, otherwise your cookies won't come out properly. So this is the same thing. In order to have this reaction work, for every 1 mole of oxygen, you need double or twice as much hydrogen to get these 2 moles of water out. If you don't, then you won't be able to produce as much water as expected. This is how they react and the ratios at which they react. So let's talk about the mole ratios between just 2 different elements instead of the whole, or substances. I shouldn't say elements because we have a compound in there, right? Water's a compound. So what is the mole ratio between oxygen and hydrogen? Well, oxygen is 1, so it's 1, and then this is like a comparison, 1 to 2. A 1 to 2 ratio. That's how it's written. Okay? What about oxygen and water? Well, oxygen is 1 and water is 2. So this is 1 to 2 ratio. What about hydrogen to water? Well, that's a 2 to 2 ratio, also the same as 1 to 1, okay? Right, 2 to 2 is the same as 1 to 1. So let's say you have 5 hydrogens, you also have 5 waters. Let's say you have 70 hydrogens, you also have 70 waters, because they are in the same ratio as one another. So the first way we're going to do this is conceptually, and then we're going to start using word problems. So this chart is saying, okay, this is how they react, and I tell you, in a reaction, I give you 2 moles of oxygen gas. How many moles of hydrogen then are required? Well, if it's a 1 to 2 ratio, if you have 2 here, you better have double here, right? 1 to 2 would be double of this guy, so that would be what? 4. 2 to 4 is a 1 to 2 ratio. Well, between hydrogen and water, it's a 2 to 2 ratio. So whatever hydrogen is, water is the same. So if hydrogen is 4, water is also 4 moles. Now, dimensional analysis-wise, this is what it looks like. You write down what I give you, 2 moles, and you write the substance, 2 moles of oxygen. Set up your dimensional analysis like we used to do. I know it's been a while, but since you just did your corrections, it's probably a little bit more fresh in your brain than it had been. Now, the thing you want to get rid of goes on the bottom. This is not a lot of space. So moles of O2 go on the bottom because we're trying to convert to something else. What are we trying to convert to? Well, for the first one, this box right here, we're trying to go to hydrogen. So moles of hydrogen go here. This is a mole to mole ratio, mole to mole ratio. This, by definition, this specific part is what stoichiometry is. And what stoichiometry allows you to do is to jump around between different substances in a chemical reaction. So I'm jumping from oxygen over to hydrogen. So in order to do that, I have to use mole to mole ratios. Well, the mole to mole ratios come from the balanced chemical reaction. So my oxygen has a 1 in front of it. What does my hydrogen have in front of it? A 2. Two times 2 divided by 1 is 4. So this is how you do it mathematically if you can't see it conceptually, because we're doing it conceptually first because these numbers are nice. I'm giving you nice numbers. They're not always going to be beautiful numbers, as we'll see down below. Okay? So look at answer or part B. Part B says you have 8 moles of hydrogen gas. So the easy one to do is if this is a 2 to 2 ratio, whatever you have here is the same as you have here. So this is 8 moles, this is 8 moles. Let's look at that mathematically. Okay, I have 8 moles of hydrogen. Why? Because the problem says so. I set up my dimensional analysis. The thing I don't want anymore is the hydrogen gas, and the thing I do want is the water. Mole to mole ratios. This is stoichiometry. I'm jumping from hydrogen to water in the chemical reaction. So let's look. It's a 2, for every 2 moles of hydrogen that react, 2 moles of water are produced. So every 2 moles of hydrogen that react, 2 moles of water are produced. 8 times 2 is 16, divided by 2 is 8. Okay. Now, visually, what is the oxygen going to be? Well, if this is a 1 to 2 ratio, whatever you have here, this number is double that. So that's going to leave this as 4 moles. 4, and then doubled is 8. But let's look at it mathematically. I have 8 moles of hydrogen gas. The moles of hydrogen gas go on the bottom, and the moles of oxygen gas go on the top, because that's who I'm looking for. So you go back to the problem. There's a 2 mole, for every 2 moles of hydrogen gas required, 1 mole of oxygen gas is required, right? Because there's a 1 in front of the oxygen. So 8 divided by 2 is 4. Now, I know that you can do this conceptually for some of these, but you need to be able to do it this way. This is going to be the most important way eventually. Okay, being able to do this dimensional analysis. And again, this is stoichiometry, this mole to mole ratio. And it allows us to jump from one substance to another. Oops, sorry. So what can I do? I can jump from oxygen to hydrogen. I could jump from oxygen to water, hydrogen to water, water to hydrogen, water to oxygen, right? It allows you to jump around. These mole to mole ratios allows you to move around in the chemical reaction to talk about other substances. Okay, so let's do this. We'll do C, D, and E. I'll do C with you, and I'm going to have you try D and E, or sorry, D, E, and F on your own. So conceptually, if there's 3 moles here, this is a 1 to 2 ratio, so this number better be double, right? So what's double of 3? Well, that's 6. This is a 2 to 2 ratio, so if this is 6 moles, this is 6 moles. Let's look at it. Oh, sorry. 1 to 2, 1 to 2. So 3 times 2 is 6. But let's look at it mathematically. 3 moles of oxygen gas. Set up your dimensional analysis. The moles of oxygen gas go on the bottom so that we get rid of it. The moles of hydrogen gas go on the top. It's a 1 to 2 ratio. So this mole to mole ratio comes from the balanced equation. Okay. So 3 times 2 is 6. So that's why we got 6 here. And then look at, you could do, so I know when I did this one, because I did this conceptually because this was easy, that if this is 2 to 2, whatever this is, what is this? But you could start with the oxygen still. You have 3 moles of oxygen, and for every 1 mole of oxygen, it's 2 moles of water, right? So it's the same, 6. It doesn't matter which way you look at it right now. So I'm going to give you 2 minutes to please do D, E, and F. Do not do G and H yet. Please do D, E, and F. Please type done in the chat when you are finished. Okay, so this is what we have for the answers. Before we move on, do I have any questions on how to do mole-to-mole ratios, which is known as stoichiometry, mole-to-mole ratios? So someone asked for F, so I'm going to do F. So I have 0.070 moles of water. So let's do it. I'll do it right here. So the first thing you do is write out the number that's given, the unit, and the substance. Okay. So the thing we're trying to get rid of, which is water, goes on the bottom so that it cancels. And let's go to hydrogen first, for example. So this is every 2 moles of water that are produced, 2 moles of hydrogen react. So for every 2 moles of water produced, 2 moles of hydrogen react. So 0.070 times 2 divided by 2 is still 0.070. Okay? And then, let's do it again. 0.070 moles of water. And then we'll do moles of water again on the bottom. And now we're going to do the other substance, which was oxygen gas. So if you look back at the balanced reaction, for every 2 moles of water that are produced, 1 mole of oxygen gas reacts. So for every 2 moles of water produced, 1 mole of oxygen gas reacts. So this is 0.070 divided. The stuff in the bottom gets divided. Remember, it's just, I do the line method, but it's just like doing this. Okay, it's the same thing. So 0.070 divided by 2 is 0.035 moles of O2. In order to get full credit on these types of problems, you have to have that and you have to have this. You have to have the unit and you have to have the substance, if there is a substance. Okay, so let's repeat. What kind of ratios are these? They're called what kind of ratios? 1 to 2 to 2. This is 1 what of oxygen? For every 1 mole of oxygen that reacts, 2 moles of hydrogen react to produce 2 moles of water. So again, these are mole to mole ratios. So you should notice an issue in G and H. What unit is that? What does G stand for?
Grams.
Grams, okay? So you cannot do ratios in grams. You have to be in moles before you can do mole to mole ratios. Now, have you learned how to turn grams into moles? We did, right? Really early on in the year, grams to moles. So let's flash back. Okay, so this was actually on the test you just did corrections for, right? So we know how to get from grams to moles or from moles to grams. Okay, they're just reverse processes, but the same method in essence. How do we get from grams to moles or moles to grams? Molar mass. Where does molar mass come from? Periodic table. Okay, so right now we are only focusing on this part. This part is irrelevant right now. Grams to moles or moles to grams. And the reason you have to do this is because the ratios present from the balanced chemical reaction are mole ratios. They are not gram ratios. This isn't 1 gram, 2 grams, 2 grams. This is 1 mole, 2 moles, 2 moles. So if you want to do stoichiometry, you have to be in moles. All of these started up here in moles. So it was an easy 1 step, meaning this is going to be a 2-step problem. So here's how this goes. I have 54 grams of water. The first thing I have to do is convert it to moles. Let's see. So remember, the unit you don't want goes on the bottom, grams of water. And now, be careful. All of the numbers on our periodic table. So let's pull that up just really quick. All of these numbers on here. So carbon is 12.01 grams per 1 mole. Nitrogen is 14.01 grams per 1 mole. Oxygen is 16 grams per 1 mole. All of these numbers on the periodic table, these molar masses, are per 1 mole. So do not forget that. So what's water? Well, it's hydrogen. Sorry. Hydrogen is 1.01 times 2, because there's 2 of them, right? Plus oxygen is 16. You add them together, and what do you get? You get 18.02 grams for every 1 mole of water.
Yeah, so I got the answer. Do I round it?
Well, I'm not, nope. So we're not done yet. So because we're not finished with the problem, you don't round yet. Keep the whole number in your calculator. So grams of water cancel, and now we're at moles of water. Well, now that we're at moles, now we can do mole to mole ratios. So let's go back. So we're going to go, let's go to hydrogen first. So for every 2 moles of water that are produced, 2 moles of hydrogen react. Okay. So just extend this like we've done in the past. Now, the thing we don't want anymore goes on the bottom, moles of water. And the moles of hydrogen are the thing we're looking at right now. And it's a 2-to-2 ratio. And we're left with moles of hydrogen. So this is stoichiometry. This right here is old stuff. Grams to moles is something we've already done. So you just have to get into moles before you can do stoichiometry. So jumping from moles of one substance to another substance is stoichiometry. And this comes from the balanced reaction. Okay? So 54 divided by, because this is in the bottom, 18.02. Now really technically, right, this is 1 to 1. So once you divide by 18.02, you're finished. Now, this is the only numerical number given. It's 3 sig figs, so your answer needs to be 3 sig figs. Does anybody have the answer to 3 digits for me? So it's 2.9966 something something something. So it's basically 3.00. Moles. Now, technically, because you know that this is a 2-to-1 ratio, whatever this number is, whatever's in here is double. So you can probably conceptually look at this and know that this is 1.50, but I want to do the math. I want to do the practice. So I'm going to start back over with my starting point. So 54 grams of water. I cannot do mole ratios until I'm in moles. This is molar mass. Molar masses are always grams per 1 mole. And it's water, so it's 18.02 moles. This is of water. And then moles of water go down here. Now this time, we're trying to find who? We're trying to find oxygen. So I do the ratio between water and oxygen. So for every 2 moles of water that are produced, 1 mole of oxygen reacts. Again, these are our coefficients from our balanced chemical reaction. This is the stoichiometry part. Okay, so this is 54 divided by 18.02 divided by 2. So yep, with sig figs, it's 1.50. It's like 1.498 something something. 1.49831. Sorry, 1 point. So 1, 2, 3 sig figs. These will just round this up to 1.50. Okay? So let's try the next one. So what I'm saying on here is you can't do this. You can't be like, well, this is a 2-to-2 ratio, so if this is 14, this is 14. Not when you're in grams. If this said moles, yes, you could do that because these are mole-to-mole ratios. If you are in grams, you can't do ratios like that. You have to be in moles before you can do mole-to-mole ratios. So no matter what, we want to get to moles, even though it's listed in grams, because in order to jump around from different substances in a chemical reaction, you have to use mole ratios, and you can't use mole ratios unless you're in moles. So if you start in moles, you have like a head start. But if I start you in grams, you have to do a little bit more work. It's an extra step. So let's try this one. 14 grams of hydrogen gas. Okay, I can't be in grams to do stoichiometry, so I have to turn grams into moles. So grams go on the bottom, 1 mole goes on the top. This is molar mass, and it's hydrogen. Hydrogen is 1.01 times 2, there's 2 of them, so it's 2.02 grams for every 1 mole of hydrogen gas. This will get me in moles, and now I can extend this and do my mole-to-mole ratios. So moles of hydrogen gas go on the bottom. And who do I want to do first? Let's do oxygen this time first. So I'm jumping from moles of hydrogen to moles of oxygen. Okay, there's a 2 in front of the hydrogen and a 1 in front of the oxygen. So 14 divided by 2.02 divided by 2 is 3.47. Oops. So this is 3.47 moles. Okay, well, let's do water. So I'll start at my same starting point. Oops, sorry about that. I turn my grams into moles, and now I'm going to go to water instead. For every 2 moles of hydrogen, that goes on the bottom, that react, 2 moles of water are produced. Where do I get that? I get that from the balanced chemical reaction. For every 2 moles of this, now I'm jumping over here, there are 2 moles of this. So 14 divided by 2.02 times 2 divided by 2. So this in essence is a 1-to-1, right? This does nothing. So this number ends up being 6.93 moles. Okay. Any questions so far? So what happens, what if I, what was this one? Sorry, what was the oxygen gas? 3 point, was it 3 point? Ooh. Was it 3.47? So sometimes I get this question. I get, well, if you get this one in moles, can you just take this number and do mole to mole ratios to do this instead of starting all the way back over from the beginning? And that answer is yes. So look, I will show you. If you want, once you get one of the substance's moles, you can use that guy, the 3.47, to find the moles of anything else. Once you have the moles of one substance, you can just use mole to mole ratios. So instead of starting from 14 grams all over again, grams to moles, moles to moles, let's look at it this way. This is what we determine the moles of oxygen to be. So what we can do is we can say, okay, well now I'm going to just do mole ratios from oxygen to water. So what's that ratio? Well, that's a 1 to 2 ratio. 3.47 times 2 is 6.93. So either process gets you the same answer. Meaning it's not going to matter which way you do it. However, initially, at the very beginning, you must turn this into moles before you can go anywhere. All right. We are going to do these practice problems. These are word problems now instead of like in a box. So here's how I do this. I tend to do this with numbers. So how many moles of hydrogen gas, so that's this guy, are needed to react with 3 moles of oxygen gas? Well, that's this guy. So the number I give you belongs to oxygen. So the first thing you do, write out what I give you. 3.0 moles of oxygen gas. Always write that out. You can at least do that. Set up your dimensional analysis. You can at least do that. Since I'm already in moles, I can instantly jump to the other substance's moles. So moles of O2 go on the bottom. And who do we want? Well, we want the hydrogen gas. So we're jumping from here to here. It's our mole to mole ratio. For every 1 oxygen that reacts, 2 hydrogen react. So 3 times 2 is 6 moles of hydrogen. Okay? I'm going to skip B for now. Let's go to C. So, how many moles of water, so this is who we're asking about, can be produced, right, because it's a product, from 4 moles of hydrogen? Well, that's this guy. So I'm jumping from hydrogen over to water. So the first thing you do, write out what I give you.
Right. Think of something different.
Okay, so moles of hydrogen. Moles of hydrogen go on the bottom because we're trying to get rid of it. And the thing we want, which is water, moles of water go on the top. So for every 2 hydrogens, there's 2 waters. 4 times 2 is 8. 4 times 2 is 8. Divided by 2 is 4. So it's 4. Again, you must write the word mole and you must write the substance, water, to get full credit. Okay. So let's try this last mole to mole problem. So 5.5 moles of water. So that's this guy. Okay. How many moles of oxygen? So that's this guy. So I'm jumping from water over to oxygen. So moles of water go on the bottom, moles of oxygen go on the top. For every 2 moles of water that are produced, 1 mole of oxygen react. So the answer is 2.75. However, this is only a 2 sig fig number, so 2.8 moles of oxygen. Oops. Okay. Any questions on mole to mole ratios right now? We're going to do some more practice. All right. Let's balance this. So this is the first example where I have not balanced it for you. So let's practice balancing this together. First thing, what type of reaction is this? A hydrocarbon in the presence of oxygen making carbon dioxide and water. This is a what?
Combustion.
Combustion, good. So let's see, 4 carbons, so I have to put a 4 here for 4 carbons. 10 hydrogens, so I have to put a 5 here. Now the oxygens are tricky, so listen to this trick. In fact, please make a note. 4 times 2 is 8, plus 5 is what? 13? Put 13 here, but this is 13 times 2, right? So put the 13 here and then multiply everything by 2. The reason that is because what you would do is you'd really write 13 halves, O2, because 13 halves times 2 is 13, right? But we don't want to leave fractions in there, so to get rid of this fraction, we would multiply it by 2. But if you multiply one chemical by 2, everything needs to get multiplied by 2. Oh, whoa. Okay, so how many moles of carbon dioxide are produced? So that's this guy. Why does it keep doing that? And then I give you 5 moles of oxygen gas. So write out what I give you. That's this guy. So the thing we don't want goes on the bottom. And so we're jumping from oxygen gas to carbon dioxide. This is a 13 to 8 ratio. So this is not a very nice ratio. So 5 times 8 divided by 13 is how you do that. This is a 2-digit number, so our answer needs to be 2 digits. So I got 3.1. Is that what you got? It's 3.0769 moles of carbon dioxide. Okay? All right, last one before we move on. 3.00 moles of O2. Moles of O2 go on the bottom, and I'm trying to find moles of water vapor. Why do you think they call this water vapor? Because water is, go ahead, Nathan.
Never mind. I'm reading kind of three right now.
It's because water is a gas. Gases are often referred to as vapors. Okay? So 13 for the oxygen and 10 for the water. So 3 times 10 divided by 13. Now 3.00 is 3 sig figs. So your answer needs to be 3 sig figs. So I get 2.31 moles of water. Okay. So let's do example 4. So aluminum oxide decomposes into aluminum and oxygen gas. The first thing you need to do is balance this, please. I'll give you a second to balance it. Okay, 2 to 4 to 3. So this asks, what is the mole ratio of aluminum to oxygen? Well, aluminum to oxygen is a 4 to 3 ratio. And this first part says, how many moles are in 204 grams of aluminum? Or aluminum oxide, excuse me. Well, this is old stuff. Grams to moles. How do we turn grams to moles? Molar mass, right? So 204 grams of aluminum oxide. Now look, I cheated and calculated the molar mass. So aluminum times 2 plus 16 times 3, because there's 3 oxygens, gives you 102. So grams per 1 mole, remember? So 102 grams for every 1 mole is what? It's 2, right? Now, sig figs, 2.00 moles, because this is 3 digits. You don't get to just write 2. That's wrong. Aluminum oxide. So the question is how many moles of aluminum this guy can be produced, and I give you grams of this guy. So I have to jump from here over to here. So how do you do this? Well, we've already done this, right? You turn grams into moles. Oops. Sorry. Let's see if I can. So grams into moles first of aluminum oxide. How do you do that? Molar mass, 102 grams for every 1 mole. And then once you're in moles, then you can do the stoichiometry. So the moles of aluminum oxide go on the bottom because we don't want that one anymore. And the thing you're trying to find goes on the top, which is aluminum. So it's 2 moles of aluminum oxide for every 4 moles of aluminum. Can you call this 2 to 1 instead? And that answer is yes. If you want to reduce that fraction, you're welcome to. It doesn't matter. I'm not going to. I'm just going to leave it like this. 204 right here divided by 102 times 4 divided by 2. Is it 1? Oh, sorry. I lied. It's 4, right? 4 moles of aluminum. 204 divided by 102 is 2. 2 times 4 is 8. 8 divided by 2 is 4. So then I'll get the question, well, if I already found moles here, Couldn't I have just done mole to mole ratios from here? Yes, you could have, but I'm trying to practice the long way with you. Okay, last one for the day. So we've done this. This was early in the first semester. You can go either way, right? This is from molar mass. Now, what we learned new today was how to go from moles of one substance to moles of another, some other substance, right? This is stoichiometry. This is the balanced reaction. Rxn is reaction. So we've gone from grams to moles, moles to moles, okay? We've also just done moles to moles. We've gone from here to here and here to here, okay? And we've also done the 2 jumps. But now we can also go back to grams of the other substance. So just like grams to moles, moles to grams is molar mass from the periodic table. Okay, so let's practice. How many grams of tin 2 fluoride are produced? So tin 2 fluoride is a product, and I give you grams of hydrofluoric acid. So first thing you have to do is write out the reaction. Hydrofluoric acid is HF. It's being mixed with, so that's plus, a piece of tin, that's SN. All right, so I will give you a second. You need, what kind, first of all, this is why being able to predict products is important, because you can't do this problem if you can't write out a balanced reaction. So hydrofluoric acid is mixed with a piece of tin. What type of reaction is this? A compound with a single element. So take a moment to switch partners. So the tin's gonna come in and kick off the hydrogen, right? Metals like to be positively charged, so the positively charged thing will be replace the other positively charged thing, and hydrogen is the +1, -1, okay? So they already tell you who one of the products is, tin 2 fluoride. So tin is +2, fluorine is -1, so this is how they go together. Now, who's the other product then? Hydrogen gets to be by itself. Now, is this how hydrogen exists when it's by itself? No. You have to write it as a diatomic. So, right, we're tying in what we've been learning to this new stuff. So, now you need to balance. So I needed 2 here because there's 2 fluorines. That gives me 2 hydrogens, 2 hydrogens. Okay. So the mole ratio is 2. There's an invisible 1 in front of here, right? 2 to 1. And there's a visible 1 in front of here. And there's an invisible 1 in front of here, in front of the hydrogen. Okay. So let's talk about what we have and what we need. So we have 30 grams of hydrofluoric acid. So we have this number. And they want to know grams, not moles, grams of tin 2 fluoride. So that's this guy. So I have to, in essence, jump from HF over to tin 2 fluoride. The only way I can do that is with mole ratios. So if I'm in moles, I can start off with mole ratios, but I'm not. I am in grams. So here we go. So we need to turn grams to moles for HF. So you take a hydrogen, which is 1.01, and you add a fluorine, which is 19. So what's that? 20.01 grams per 1 mole, right? So grams per 1 mole. This is molar mass of HF, 20.01 HF. Okay. Now we're at moles, we can do mole ratios. So the moles of HF go on the bottom because we don't want it anymore. The thing they asked about was the tin 2 fluoride, which is SNF2. So let's go back to the reaction. For every 2 moles of HF that react, 1 mole of tin 2 fluoride is produced. So for every 2 moles of HF that react, 1 mole of tin 2 fluoride is produced. Now, until now, we were stopping here, but they actually asked you for grams, so we have to do one more step. Now, this step isn't new. You should be able to convert moles to grams because we do that using the periodic table. So remember, we're at moles, right? So mole goes on the bottom, and gram goes on the top. Now, molar mass is always for 1 mole. All of the numbers on the periodic table are for 1 mole. So let's look. We have tin, tin is SN, so 118.71. So I'll just do this over here. So tin is I already forgot what I said. 118.71. So tin, and then it's 2 fluorines, right? Fluorine is 19, but there's 2 of them. Add them together. $156.71. So, do you do the whole math? 30 divided by 20.01 divided by 2 times 156.71. And we get, let's see, this is 3 sig fig, so our answer will be 3, so it's 117 grams of tin 2 fluoride. So what this is saying is if you throw in 30 grams of hydrofluoric acid into this chemical reaction we have, theoretically, you should get 117 grams of tin 2 fluoride out based on the ratio in which they react and produce with one another. Okay? So I would like you, I have 10 minutes left, I would like you to try example number 6 right now on your own. I'm going to give you, let's see, 5 minutes. All right, so I have our answers set up. I have the work. So A, you had to turn grams into moles, and then you could do mole ratios, and then you could go back to grams. B asked you for moles, so you needed to stop at moles. So you really need to pay attention to what unit they're asking of you. It's not always going to go grams to grams. Sometimes it won't even start in grams. Sometimes it starts in moles. So again, being aware of what what units they're starting you in is really, really important. And so you always write down what's given first before anything. And hopefully that will help set up the road for where you need to go. So your homework tonight and this weekend will be these types of problems mixed with some predicting product and word equations most likely.